We've all felt it. That invisible pull that keeps our feet planted firmly on the ground, the force that makes objects fall to the earth, the same force that governs the motion of planets, stars, and entire galaxies across the cosmos. This fundamental force, this ever-present pull, is gravity. It's a force so ingrained in our everyday experience that we rarely stop to question its true nature. Yet, beneath its apparent simplicity lies a profound mystery that has captivated scientists for centuries. From the moment we take our first steps, we learn to navigate a world governed by gravity's constant influence. We throw a ball, and it arcs gracefully back down to Earth. We jump, and gravity inevitably draws us back to the ground. This invisible force shapes our world, dictating the rhythm of ocean tides, the flow of rivers, and the elegant dance of celestial objects in the vast expanse of space. But what exactly is gravity? How does this invisible force exert its influence across such vast distances, holding our planet in orbit around the sun and sculpting the large-scale structure of the universe? For centuries, these questions have fueled scientific inquiry, leading to groundbreaking theories that have revolutionized our understanding of the cosmos. From Isaac Newton's groundbreaking law of universal gravitation, to Albert Einstein's mind-bending theory of general relativity, our understanding of gravity has undergone a profound evolution. Yet, despite centuries of scientific progress, the true nature of gravity remains one of the most intriguing and enduring mysteries of our universe. In the 17th century, a young Isaac Newton, contemplating the nature of gravity, had his legendary eureka moment. Legend has it that while observing an apple falling from a tree, Newton had a flash of insight. Could the same force that pulled the apple to the ground also be responsible for the moon's orbit around the Earth? This simple yet profound question led Newton to formulate his groundbreaking law of universal gravitation. This law, published in his monumental work Philosophiae Naturalis Principia Mathematica in 1687, stated that every object in the universe attracts every other object with a force directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. In simpler terms, Newton's law tells us that objects with more mass exert a stronger gravitational pull. That's why the Earth, with its massive size, keeps us firmly planted on its surface. The law also states that the farther apart two objects are, the weaker the gravitational force between them becomes. This explains why the Moon, despite its smaller size, still exerts a noticeable gravitational pull on Earth, causing tides. Newton's law, expressed in its elegant mathematical form, provided a simple yet powerful explanation for why objects fall to the ground, why planets orbit stars, and why the universe hangs together as it does. It was a revolutionary concept that unified the heavens and the earth under the umbrella of a single universal law. Newton's law of universal gravitation was more than just an elegant equation. It was a triumph of human ingenuity, a testament to our ability to decipher the universe's hidden code. For the first time in history, humanity had a mathematical tool that could accurately predict the motion of celestial objects. The law's predictive power was astounding. Astronomers used it to calculate the orbits of planets with unprecedented accuracy, confirming the heliocentric model of the solar system and putting to rest centuries of debate. Newton's law also explained the observed variations in planetary motion, previously a source of much confusion and debate. Beyond our solar system, Newton's law revealed its true power. Astronomers used it to discover new planets, predict the return of comets, and even weigh celestial objects. The discovery of Neptune, the 8th planet in our solar system, stands as a testament to the predictive power of Newton's law. Astronomers, noticing irregularities in Uranus's orbit, hypothesized the existence of an unseen planet whose gravitational pull was perturbing Uranus's path. Using Newton's law, they calculated the hypothetical planet's location, leading to its discovery in 1846. Newton's law wasn't just about explaining the cosmos, it was about understanding it. It provided a framework for comprehending the fundamental forces shaping the universe, paving the way for future scientific advancements. However, as successful as Newton's law was, it wasn't the final word on gravity. The universe, as we would later discover, had more surprises in store.